So in this video, we'll be talking about mobility of a mechanism. Now, we'll be looking at this from a couple different perspectives. One is from an intuition perspective, so saying, all right, let me go back to the skid steer that I had before, where I can look at it and say, intuitively, I can start to understand how many degrees of freedom it has. Then we'll also be using a little bit more robust method called Grubler's equation to describe how many degrees of freedom a mechanism has based on the number of links and then the type of joints that it has on it. So let's first of all talk about mobility from a degrees of freedom standpoint and formalizing this. So degrees of freedom of a mechanism is simply how many independent inputs it needs to completely control its motion. So with this skid steer example, you'll notice that I have two hydraulic cylinders, this one down here and this one up here on the bucket. Therefore, you would expect that this has 2 degrees of freedom, which it intuitively does, and by Grubler's equation we'll show in a moment that it does have 2 degrees of freedom. So I have one input for the lifting, which would be this cylinder here, and I have one input for the tipping of the bucket, this cylinder here. Or you'll notice that I actually have pairs of cylinders, but we're looking at it in a single plane and therefore consider it just the cylinders in that of the one side of the plane that's controlling it. So we've got degrees of freedom. Now, how do I start to quantify this? Well, in planar motion, meaning that we're in a single plane, we only allow x, y, and rotation. When I'm looking at it in a single plane, anytime I take a link, let's say this link right here, and I place it on a plane, I add 3 degrees of freedom. What are those 3 degrees? Well, I've got x, I've got y, and I've got rotation as my 3rd degree of freedom. So anytime I add a link, I'm going to say I'm adding 3 degrees of freedom. Now, we do have to note that I'm always counting ground as my first link. So when I've got my count here of 3 degrees of freedom, there is 0 degrees of freedom for ground. So we just have to be careful of that and take that into account when we are calculating the number of degrees of freedom of a mechanism. Now, anytime I add a full joint, and what I mean by a full joint in a planar world would be something like a pin joint. So I have a pin right here. I'm going to place it through my link. I added this link, it added 3 degrees of freedom. I'm now adding this full joint. This full joint is going to remove 2 degrees of freedom. So now I have just a single degree of freedom left. I added 3, I took away 2. Now we also have the option of adding half joints in some cases. Half joints would be the roll slide pairs, and those only remove 1 degree of freedom. So let me put all this into an equation to describe this, and this is Grubler's equation. So you'll notice Grubler's equation really follows that same set of bullets that I just talked through right there, where first of all I'm looking at the number of degrees of freedom. This is the number of links. F, which was originally saying, this is the number of degrees of freedom. This is equal to 3, which is the number of degrees of freedom added by each link, times n minus 1. The reason I'm subtracting 1 is because ground has no degrees of freedom. And then I'm subtracting off 2 times the number of F1 joints. F1 joints, these are the number of full joints. Number of full joints. And then I'm subtracting off 1 for every half joint. So this is the number of half joints. And that is Grubler's equation, which is very simple, but allows us to describe the degrees of freedom of mechanisms where sometimes intuition can get us there, but sometimes it's a little bit more difficult to work through that. So let's actually look at this example right here. So this is the kinematic diagram that I created in our last video lecture, and I've just changed it to blue in this case so I can draw on it in red and make it look a little bit different. But I'm going to now do a Grubler's equation analysis of this to determine how many degrees of freedom it has. So we had previously counted up the number of links that I have, and we had decided that I have 9 links. Again, ground being 1, 1, 1, and then I had 2, 3, 4, 5, 6 being that side of the cylinder, 7, 8, and 9 being the bucket. So as I write this out, I get 3 times 9 minus 1, and then I'm going to subtract off 2 times the number of full joints that I have. So these would be the pins or the slider joints that I have. So if you remember, I added all the way up through K. Well, that is 11 if I count correctly. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 2 times 11. And then I subtract off 1 for every half joint I have. Now in this case, I don't have any roll-slide pairs, so I have 0 half joints to subtract off. So my number of degrees of freedom here is 8 times 3, so 24, minus 2 times 11, or 22, or 2 degrees of freedom. So a fairly simple example that intuitively we were able to say that same thing, and then I move off to this way of quantifying it numerically, and I can say the same number of degrees of freedom. Now when we get to a little bit more complex mechanisms, we can take this intuitive method a little bit farther. And what I mean by that is I'm going to take my linkage and I'm going to look at the links that are connected to ground, and I'm going to start removing those degrees of freedom individually. So imagine that I take this mechanism right here, and I'm going to look at this pin joint and say, this pin joint is now, instead of this pin joint having rotation, I'm going to remove the degrees of freedom for this pin joint and see if it still is mobile. So once I remove the degrees of freedom for this pin joint, now I move up here, and this then becomes ground. Now, because this is ground and I've got connection from here up to this point and back to this point, I basically have 2 grounds right here. That forms then a truss mechanism or a structure. So I know that this lower section is no longer mobile. So by removing this 1 degree of freedom, I have removed all the mobility of this lower section of my mechanism. But I still do have mobility up here, so I at least have 2 degrees of freedom. So now I'd move up to this part of my mechanism and say, let me remove another degree of freedom, perhaps fix this pin joint, in which case this point and this point are now across from each other, and say, do I still have mobility? Well, in that case I don't, because my hydraulic cylinder would not be able to move. So I would go to 0 degrees of, or no additional degrees of freedom. So that's an intuitive way of walking around a more complex mechanism and removing each degree of freedom individually and say, do I still have motion? If I do, then I at least have that number of degrees of freedom. So a couple of different ways of approaching this. You'll look at a few more complex ones in class as an example. Now, Grubler's equation works most of the time. There are a couple of exceptions, and I put exceptions in quotes because you'll see why in just a moment. Well, let me look at this mechanism right here, where I can say, all right, how many degrees of freedom should I have? And I can say F is equal to 3 times the number of links that I have. In this case, I've already got them numbered for you, 5. 5 minus 1, minus 2 times the number of full joints that I have. And I've got A, B, C, D, E, and F, or 2, 4, 6. So 2 times 6. And I've got no half joints. So here I end up with 4 times 3, or 12, minus 12, or 0 degrees of freedom. And you look at it and say, yeah, that makes sense. It would be a 4-bar, except that I have that link 5 up there, which is keeping this from moving back and forth. Now, what is the exception? Well, the exception is, what if I, again, make a 5-bar mechanism, but set it up in a way that geometrically it's still going to move? So you'll notice on the bottom here now, I have created this parallelogram mechanism where I have links 2, 4, and 5 all being of the same length, and they happen to all be parallel, so that I know I would actually have motion of this. Now my Grubler's equation is going to come out the exact same way, predicting I have 0 degrees of freedom, but because of the way I've set this up geometrically, I will get some mobility. So just be careful that Grubler's equation will not take care of these special cases. But you really wouldn't want to design and build this special case anyways. Why? Well, because you would have to manufacture this perfectly. If you had a little bit of tolerance in the length of these links or the location that these pins were placed at, you would have binding in the mechanism, high forces, and it would not be a well-functioning mechanism. So you would not want to generate this anyway. Another exception is sometimes you have an extra degree of freedom or a passive degree of freedom that you're not interested in. So imagine a cam follower, which is typically a circular element on a cam, and so it can either roll or slide on that surface. Well, you really don't care what the orientation is of that roller, but it provides an extra degree of freedom, which Grubler's equation would tell you. So just recognize that sometimes it will say, yes, you have a passive degree of freedom and you're looking for it and saying, where is it? And sometimes it'll say you have no mobility, but geometrically you might be able to have a mobile mechanism. So just taking a step back, reviewing here, we can look at a mechanism, intuitively describe how many degrees of freedom it has, and then check that using Grubler's equation by counting up the number of links and looking at how many and what types of joints that we have.